Hello everybody, and welcome to another geometry lesson. Today we're taking a look at section 5.4, which is all about equilateral and isosceles triangles. Really, the main star of the show here is the isosceles triangle, which, as a reminder, is any triangle where two of the sides, or at least two of the sides, are congruent. When you have an isosceles triangle like this, again, an isosceles, or a triangle is isosceles when it has at least two congruent sides. When you have an isosceles triangle with exactly two congruent sides, we actually have some names for the parts of this triangle. So to start off, these are called the legs, the two congruent sides. The two congruent sides are called the legs of the triangle. Now, when you have the two legs together, it makes this angle up at the top. We have a name for this angle up at the top as well, even though we don't really use it as often. This is called the vertex angle. Vertex angle. Now, we just have this side down here that's left by itself. The side that's by itself, we actually have a very familiar name for this: the base of the triangle. Think about like 1/2 base times height. We've seen that a bunch. This is that base in question. So the third side is the base of the triangle. And now here's the most important part. Down at the very bottom, you've got these two angles that I'm going to mark in red. These angles are right next to the leg and the base, and so we call them the base angles. Oh boy, these base angles can do a lot for us. So keep these in mind as we go through today's lesson. If you see base angles or you see an isosceles triangle, you know that one of the two is going to be used. Let's take a look at the following theorems. So the first of the theorems that I want to talk about is the base angles theorem. Now the base angles theorem says if you have an isosceles triangle, a triangle where two sides are congruent, then those base angles are also going to be congruent. So the theorem goes, if a triangle has two congruent sides, then the base angles are congruent. So this happens anytime you have an isosceles triangle. But we also have a converse of the base angles theorem. And as we know, a converse is like a backwards version of a theorem. And this one says, hey, if you have some mystery triangle where the base angles are congruent, guess what? You know it must be an isosceles triangle. So two of the sides are congruent. So it's the direct opposite of this. Purple proves red, purple proves red. So the converse of the base angles theorem is if a triangle has two congruent angles, then the sides opposite them, or opposite to them if you wanted to say it in more modern English, are congruent. So the sides that are across from these base angles are the same. Love it. Now you may have had a question. Mr. Strager, down here you said a triangle is isosceles when it has at least two congruent sides. What happens if it has all three? Well, then we wouldn't be having an isosceles triangle, and you'd have a type of isosceles. No, we would have an equilateral triangle. So this is where we want to talk about what equilateral means. Equilateral triangles are triangles where all three sides are congruent. And the corollary to the base angles theorem says, if this happens, then all of the angles of the triangle are congruent. It's equiangular. If a triangle is equilateral, then it is equiangular. Now, what would the converse to that be? So we have the corollary to the base angles theorem, and then we have the corollary to the converse of the base angles theorem. Well, converse means opposite, so what's the opposite of the one up above? That would only make sense if we already knew that all the triangles' angles are the same. The corollary to the converse of the base angles theorem says, if a triangle is equiangular, then it is equilateral. Boom, boom, boom. Love it. So let's use these four theorems in conjunction with each other for example 1. So example 1 says, use the diagram below to fill in the blanks. Example 1 starts off with, if AE is congruent to DE, then blank. This is an important time to take a look at what sides are being referenced. So I'm going to color AE in blue, and I'm going to cover DE in blue. There we go. So these two make a blue triangle that sort of encompasses the whole diagram. If we are told that AE is congruent to ED, what could we conclude? Well, this is an example of two sides of an isosceles triangle being congruent. And the rule is, if a triangle has two congruent sides, then the base angles are congruent. So we could say angle A is congruent to angle D. Now I will warn you, this diagram will get a little more complicated as we go along. Let's start that complication with the second part. What if AB, so this side right here, is congruent to EB? Well, then we would have a big old triangle in purple like this. On this purple triangle, I'm going to mark AB like so and EB like so. What could we conclude? Well, again, we have an isosceles triangle here because the two sides are congruent. And the rule is, according to the base angles theorem, if a triangle has two congruent sides, the base angles are congruent. So what would the base angles be here? Well, this one's easy because it's just angle A. But how would we name this angle up here? Since point E has a lot of angles coming off of it, we would need to use 3 letters to name it. So I'm going to name it AEB. We could say A is congruent to AEB. Cool. Let's move it along. What if D is congruent to CED? Well, D is this angle down here. I'll mark it with 3 tick marks. And CED would be the angle with a vertex at E. So now we're talking about this triangle on the right. For this triangle on the right, what could we show? Well, now we know the base angles are congruent. And the rule is, if a triangle has two congruent angles, then the sides opposite them are congruent. This is the converse of the base angles theorem. So it says if we have these two angles, then the two sides are congruent. But be careful with the order. D is congruent to CED. So anytime we see the letter D, it has to match up with the letter E. So if I call one side CD, remember the other side has to match up so that D matches with E. E has to come second. So CD is congruent to CE. Very nice. Now, to finish off, let's take a look at the last one. If angle EBC, this angle right here in the middle, is congruent to ECB, then what could we conclude about the green triangle? Well, at this point, we already sort of know. If the angles are the same, then the sides are the same. So we could say that side EB is congruent to side EC. Very nice. Cool. Let's flip over to the next side where we have example 2. And for example 2, I want you to time yourself. See how long it takes and see if you can get this problem solved in under a minute and 30 seconds. Find each angle measure in this diagram. Pause the video and try it. Hopefully you're able to give that a shot, see about that time trial. There's a reason why I didn't give a lot of time for this one. It's because this problem looks impossible. How can you find the angle measures of a triangle when none are given? But then we do notice something. Triangle PQR is equilateral. So if triangle PQR is equilateral, what can we conclude? Well, any triangle that is equilateral is equiangular, and that's by the corollary to the base angles theorem. Okay, so what? So what if all the angles are the same? Well, it does matter. All triangles must add up to 180 degrees. So if I have this one is x, this one is x, and this one is x, x plus x plus x equals 180. Or 3x equals 180. X has to be 60 degrees. So if you ever have an equilateral triangle, all the angles are 60 degrees. And we show it by saying, if a triangle is equilateral, then it's equiangular. Nice. Next up, we have some diagrams, and these ones are a bit trickier to understand since there are two triangles at play. If you really need to, you can redraw these triangles separately. I just wouldn't recommend it because it makes the relationships between them harder to see. So let's take a look. On this, we have an equiangular triangle here, KLN. This triangle, we have two angles that are the same, but not the third one. And then we have our big triangle. Well, we can use one of the lessons that we just talked about. Anything that's equilateral is equiangular. Wouldn't the opposite work too? In fact, the corollary to the converse of the base angles theorem says, if you see that all the angles of a triangle are the same, the sides of the angles are also the same. All three of these sides are congruent. But that means that y and 4 would have to be the same thing. So y equals 4, because they're congruent to each other. Very nice. Now, let's take a look and see if we can find x. X is on this weird triangle where two of the angles are congruent. Two base angles are congruent, in fact. Well, if we have two angles that are the same, according to the converse of the base angles theorem, then the sides must be the same. So these two must be the same. Wait a minute. Didn't we say that all the sides of this equilateral triangle, including this one, are 4? So if this side's 4, and this side is 4, and this side is 4, 4 has to be congruent to x plus 1. So if 4 equals x plus 1, can't we just subtract 1 from both sides? X equals 3. So my recommendation is start with an equilateral or an equiangular triangle and solve that. Then use the information on the second triangle. Let's try out B by pausing the video and giving it a shot. How'd you do, folks? This one's a bit trickier. A lot of people might recognize that the sides of this triangle, I'm going to mark in green, are all congruent. So this is equal to 5y minus 4, and this is equal to 5y minus 4, and this is equal to 5y minus 4. But then get stuck when they realize you can't set 5y minus 4 equal to 3x minus 5 and solve it. Instead, remember what I said. Once you've identified all the stuff with the equilateral triangle, move to the isosceles. How do we know it's isosceles? Well, because of the base angles being congruent. So we know that this side, y plus 12, has to equal this side, which, hang on, didn't we call that side 5y minus 4? The idea is set both of the y expressions equal to each other and solve, then plug in the y to solve for x. Last but not least, we have example 4. Example 4 is a Mongo proof, but despite the fact that the proof is very large, it's actually not a substantial proof. By that I mean there's not a lot of logical reaching we need to do, just a lot of itty-bitty mini steps. This is a proof that tests your ability to be precise. Work your way through this proof. If it takes you less than 9 steps, you missed something small. In fact, to be honest with you, we should probably technically do this proof in 10 steps, but I'll say 9 for the ease of use. So pause the video, try this proof out, see what you can do, and then check in with the answer key I'll put up on the board. And here it is in all of its 9 steps of glory. So I want to talk through each step here so you can understand how one would get all these steps. The first thing that we notice is this. If you notice that 2 sides of a triangle are congruent, you know it's isosceles. So angles C and B have to be the same due to the base angles theorem. I chose to switch it to the measure of angle C and the measure of angle B to prepare us for the next step, which is, now we have expressions for all 3 angles. Angle A, C, and B are all included in this proof. So the triangle sum theorem says all 3 of these angles have to add up to 180. A plus B plus C. But we said that A is 60 degrees, so we can substitute that in. And we also said that C is the same as B, so we could change C into the measure of angle B with substitution. Why did we do all that? Because now we only have one variable, one unknown. If we could find the measure of angle B here, we'll be golden. So that's what we do. We subtract 60 from both sides and combine the 2 B's into 2 measure of angle B's. We divide it by 2 on both sides to get the measure of angle B equals 60. So this top one's 60, and this side one is 60. According to step 3, C and B are equal. So if B is 60, then C is 60. That's what we do with the transitive property. Now, this next step is a bit of a jump, but what do we have? we have a triangle where all three of the angles are congruent. That's an equiangular triangle. So what we've shown in steps 1 through 8 is this is an equiangular triangle. We know from our postulates and theorems before that if a triangle is equiangular, then it's equilateral. And that's what we're trying to prove. ABC is equilateral because of the corollary to the converse of the base angles theorem. Thank you so much for listening, everybody. Have a fantastic rest of your night.